Okay, so week 2. Let's do a quick recap, as usual, of what we've been up to. So last time, we got introduced to sets and functions. And I tried to convince you that these are the basic mathematical objects that almost all of mathematics is built on. So you will be seeing them all the time. And today, we're going to be talking more about sets and things you can do with them. So ways to combine sets, ways to make new sets out of them, things like this. So let's start by, just for good measure, let's recall what is a set. A set A is an unordered collection of objects. Which we call its elements. And I guess another important definition was a subset, which I won't write down, but remember a subset was a set with some of those elements, right? So it's another set where every element of that is also an element of A. So we're going to start with a good way of visualizing sets that you have almost undoubtedly seen before, which is called a Venn diagram. So it's a way of graphically representing relationships between sets. And this is just some person's name. Venn was some old-timey person. So what is a Venn diagram? Well, you will get the idea by seeing some examples. Basically, you're just drawing sets as blobs and looking at where they overlap, what's inside of them, what's outside of them, things like that. So when we're drawing a Venn diagram, we will usually be working inside some universal set, or what should I call it? Yeah, universal set, which is just basically all of the objects that we're considering at the moment. So I'm not saying that there is some universal set for all the time that all sets live inside of, but I'm saying that usually when you're working with some sets, there is some universal thing that they're all contained in. So for example, you might be working with sets of real numbers, and the universal set would be the real numbers. So this is just all the sorts of elements that we're considering. And inside this universal set, we have one or more smaller sets, and we can draw them with overlaps to show that they might have an intersection and things like this. So this is probably the most familiar Venn diagram, but if you want to show something different, you can draw them different ways. So for example, if B is a subset of A, remember we use this Scoopy less than to denote that, then you might draw a Venn diagram that looks like this, where A is some set here, and B is a smaller bubble inside of it. And that shows that B is inside of A, it's a subset, right? So these are nice ways to draw pictures when you're working with sets. So let's now introduce some of the basic set operations. The union of two sets A and B is, first of all, denoted by A cup B. And let me write it in set builder notation, is elements X such that X is in A or X is in B. And you will remember this little notation, which is used to denote that it is an element. And also let me point out, of course, as always, or means inclusive or, so it means or both. So let's draw a Venn diagram to represent this. So this is our universal set, and here's A and B. Then let's shade the set that is the union of A and B. So it's everything that's contained in A, or in B, or in both, right? So it looks like that. This is A union B. The sort of dual operation to this, we've seen many operations that come in pairs, you know, and you will notice many patterns. So this is another one. We've seen and or, we've seen for all and there exists, we've seen now union and intersection. The intersection of A and B is denoted A cap B, a little upside down thing. And it's exactly the same definition, but we just replace this or with an and. And that should give you, already a good idea that these are going to operate and relate to each other in a very similar way that and or do. So again, in set builder notation, it is elements such that X in A and X in B. So another Venn diagram. Here's A, here's B. And the intersection, of course, is the place where they overlap, because these are the elements that are in both sets. So now this is A intersect B, shaded. Excuse me. And one more piece of terminology before we do some examples. A and B are said to be disjoint if A intersect B is empty. So two sets that do not intersect, which is to say whose intersection is the empty set, they are called disjoint. So let's get some examples in here. So for example, the integers can be written as this little set builder thing. So this is take every integer and include in the set twice that integer. So this is the evens. Union these things, which are odds, right? Because they form 2n plus 1. So the integers is equal to the union of even integers and odd integers. Which is to say that every integer is even or odd. On the other hand, if we take the intersection of these two sets, we get the empty set. Because no integer is even and odd. So in fact, I probably won't use this language a lot, but when you have one set that is a union of two other sets, which are disjoint, you can call that a disjoint union. So you could say that Z is the disjoint union of even integers and odd integers. That is something that you may hear from time to time. On another example. So if we take real numbers that are non-negative and real numbers that are non-positive, we get all real numbers. So R is the union of non-negatives and non-positives. And if we take these two sets and intersect them, these ones do have an intersection, which hopefully you can guess what it is. Well, let's check what it is. If you have a real number, which is greater than or equal to 0, and also less than or equal to 0, then it must be 0. So the intersection has one element, it is 0. So in particular, it's not empty. They are not disjoint. You can also have, of course, sort of easier, silly examples, like if you have what is the union of the rational numbers and the real numbers. Well, this thing is a subset of this thing, and if you ever take a union like that, you will just get the bigger thing. And similarly, if you take the intersection of something with a subset, you will get the smaller thing.